What's up, guys? We're going to do topic 3 from your holiday packet. It's titled Exponential Decay. Now this section is a lot like the last set of notes on exponential growth. There's just really one tiny difference in the formula that we're going to use, and we're going to kind of figure out why that is in this first example. So what we want to figure out today is how we can use exponential functions to represent real-world decay models. And that word decay is important because it means breaking down. You've probably seen that before. Decay is something that starts to deteriorate over time. So decay is when we're going to start with something and slowly it's going to diminish. We're going to have less of it as time goes on. So let's look at our first example. A radioactive substance decays, so we know we're dealing with exponential decay, at a rate of 3.5% per hour. What percent of the substance is left after 6 hours? Well, let's make a table just like we did with our exponential growth. So in our table, we'll make sure that we have hours and we have how much of the substance is left. Now at the beginning of this time, before we begin counting down, we have 0 hours and we have 100% of the substance, meaning we have the whole substance. So that 1 represents how much of the substance we have, all of it. After 1 hour, we're going to take that whole amount and we're going to subtract from it 3.5% of that amount. So here we've got represented the whole amount and it's decaying, so we're subtracting 3.5% of that whole amount right here. Now what we can do here is calculate it, but that wouldn't really help us because we want to see a pattern emerge. So I'm going to group them and factor them. We can't double bubble this, obviously. We're going to use just our factoring method. What could we pull from this term that we could also pull from this term? Now in this case it's a 1, and usually that doesn't help us much, but let's see what happens when we divide by 1. 1 divided by 1 is 1, and 1 times 0.035 divided by 1 is just 0.035. So we condense this to 1 times 0.965. Alright, so that's after 1 hour. Let's see what happens after 2 hours. Well, we're still going to have this 1 times 0.965. That's what we have currently. But we're going to take 3.5% of that away. And we can do the same thing we did in the last example now. We could calculate this, but we don't want to. We want to see the pattern. So now I can not just pull a 1 out, but I can pull a 1 times 0.965 out from both of these terms. And when I do that, I'll have a 1, let me use blue, 1 times 0.965 on the outside, and when I divide this term by 1 times 0.965, I get 1, and when I divide my second term by 0.965, I get 0.035, which equals 1 times 0.965 times 0.965, or 1 times 0.965 squared. And now you guys are going to start to see the relationship between our exponent and the time that's elapsed. Remember, there's really a 1 there. 1 hour has passed. All right? So it doesn't really matter at this point how many hours we choose. T hours later, we're going to have 1 times 0.965 to the t power. And we're asking for 6 hours later, so let's make that calculation now. We're going to have 1 times 0.965 to the 6th power, which equals approximately 0.808. So that's how much of the substance is left at this point, which you could rewrite as about 80.8% if you want to look at it like that. So after 6 hours, there's about 81% of the substance that's still left, and that's when we start to see the effects of exponential decay. Now the things aren't growing, they're decaying, so at the end of our amount of time, we have less of them. So let's see how different our formula is from exponential growth. It's really not too different. The amount is what we're looking for. We're going to start with our principal amount, which is what you begin with. you start with 1, a whole amount of whatever it is, but you're going to take away the rate, which in this last case was 3.5% or 0.035, and raise it to the t over n power. Remember that t is your time, and n is the number of times that it decays in that amount of time. All right, so there's your video on the front page of that, and now we'll do a video on some of the examples from the second page of the notes on exponential decay.